Thank you, Jimmy. Great presentation, Yoshi. Great use of EKS, ASG, and CRD. So we are KUNGFU.AI. We are a specialized boutique AI consulting firm. We delve in computer vision, NLP, time series, and anomaly detection. A lot of our engineers are ex-Apple, Google, AWS, SpaceX, and other places. We have a bunch of principal machine learning engineers here. Michael doubles as director, given the context. So we have kind of laid out today's presentation in three parts. So motivating, why machine learning engineers need to keep up with papers and tools that are available on the hamster wheel of, papers and tools that are becoming available on an everyday basis. So I'll give a few examples of that, and then I will let my peers introduce and delve into the details there. So first example that I just wanted to point out is this tool from UCLA called Pylon, which is a library which is Python and PyTorch compatible. So it's a declarative way of introducing constraints in your model. And you define that as a loss and you add it to the loss function. They use tnorms and you're able to basically solve that as a combinatorial solution and converge pretty quickly. You can go to the website. I'm just going to go through this really quickly because we are, kind of packed in terms of agenda. So you can, there are several examples there. The example on the right is actually a Sudoku solver. So they try to do a uniqueness check. So in your rows, your columns, and your diagonals are unique, and how you might introduce that to your loss and proceed. So the next one, this is, really taken out of the Connext for 2020's paper, which is a very readable paper and very highly implementable paper. And we are using in one of our projects with Swin Transformer as the backbone. So this is the case where we have vision transformers and sort of convenuous Connext coming together. So they've basically taken inspiration from Swin Transformer.
Hey,
yes.
Sorry to interrupt. Someone said in the chat that asked if we could make it full screen to increase the text size a little bit.
Yeah, sure. Yeah. So if we go back, so if the right was the Sudoku solver, good call out. Thank you. So this is basically trying to give the motivation that in our computer vision projects, we've mostly moved to transformers, vision transformers, and the two papers that we are all incredibly familiar with at this point. An image is basically a 16 by 16 token, and this Connext for the 2020s paper. So as I was saying, we are trying to implement Connext for 2020s in one of our projects. And so this is a very readable paper, and all the techniques that are mentioned here are easily implementable, especially patchifying using the bigger kernel and replacing layer norm with batch norm. And this is sort of the approach we are taking and proceeding. And also, I want to mention, at least Michael and myself, we've leveraged deep speed in one of our computer vision projects. And this, again, is a great way of leveraging PyTorch framework. All that is required is that you have the model written with torch.nn, and then you're basically able to wrap the model and initialize it and subsequently use it. There's a config aspect to it, and then you just reference the wrapped model in your code, and here's an example of it. And here's the config example. As you can see, zero optimization is set to true. This comes from the Microsoft research paper, and this is available both in PyTorch and Hugging Face. With that, I will transition to Michael, who's going to talk all about Potluck.
All right. Awesome. So thanks, Priya. Yeah, so Potluck, as you probably gathered from listening to Priya, we touch a lot of different areas of research. We have all sorts of different data types we deal with. And, being a services firm, we don't have one use case, one tool stack, one everything to deal with. It's all varied and depends on which client we're working with, what tools we're using. So in order to take that fact and marry it with the fact that the field is changing quickly, there's new research that comes out all the time that we need to implement, we created this tool internally called Potluck that's basically just a command line code generation tool, but it's meant to capture all this residual knowledge we get from projects. We'll go do one computer vision project over here. It's an object detection problem, something like that. And we'll learn, this really interesting way of handling bounding boxes that makes it easier to compute metrics or something like that. We have these little snippets, kind of like gists. And then we're able to bake that back into our command line code generation tool. So when we start another project, it's this, question answer type interface. It gives you a great starting point where you need to go. And then that way it's almost just like a step change from start to getting going versus, having the proverbial blank terminal. And it's also this focal point of standardization across our team. You can imagine that if everyone's doing their own thing, independently doing research on these smaller projects, there's not a lot of consistency. But if we have this tool that we're using to not only update what we think is standard, but also propagate that to the entire team, then it helps us, speak more of a common language whenever we shuffle who's working on a project with who. So it's been, great. We've gone through a previous iteration. Recently, we've just totally gutted it and redone it. And I think that it's getting close to a state that we can open source at some point. But from a philosophical level, that's kind of how we approach it. And then, we have a project template as part of that that's really standard. And, you might have a client that's really embedded in Kubeflow. They're really embedded in AWS. They have a very specific tool stack. And we do have clients like that. But we found that the only two things we can guarantee from one project to another are pretty much just a bash terminal and a Docker installation. So we really, really lean heavily into that for our project template. There's some bash scripts that do some standard things like, if you want to go into the terminal inside the container, or you want to train a model with these high level abstractions that we've come up with, all those kind of come pre-bundled with it. But otherwise, all the other nuanced differences, those are things that we can, build these templates for inside our Potluck tool. And over 2 years, we've really refined it and turned it into something that is shockingly general from one project to the next. We could do, something with like a fintech company and, build an MLOps pipeline with training, all sorts of stuff, and then take this same project template and apply it to something completely different, like a satellite imagery application with batch inference on giant images. It's still all very transferable, which is great. Next slide. And here are just a few examples of some features that we have in here. We rely pretty heavily on Fast API, which has got some dependency on Pydantic, which is really great for developing models. Most of the time, what we deliver is a microservice that's got a RESTful API wrapper around it. So, we can, that's one of these really consistent things that almost every one of our projects is going to have. We have some Terraform templates for some standard sets of infrastructure we use for various cloud platforms. It's very helpful. And then, of course, we're an ML company, so we have a lot of wrappers for some pretty common models, and that gets updated all the time, because if any of you follow research, and you see that, like with ConvNext, with what Priya just presented, and I saw some interesting stuff about Dolly this morning. There's just all sorts of crazy stuff coming out daily, so we got to keep up with it. But we do hope to open source that pretty soon, so look out for that. And with that, I'll transfer it over to Spencer.
Can we get a quick time check? How are we doing on time?
We should be doing okay. I think we've got we're 90 minutes, so probably 20 minutes max.
Okay. Wow. Well, we have more space than we thought. Well, hello. My name is Spencer Romo. I'm a principal machine learning engineer at KUNGFU. We at KUNGFU super value going and checking stuff out that we're not directly working on, because it almost always pays dividends. So last year I had a bit of downtime, and I got to thinking, it would sure be slick if I could use my machine learning skills to make money in the stock market, as I'm sure many people on this phone call have thought at time or before. And so if we move to the next slide, I eventually found this project called FinRL. It was in its infancy, and it's an open source library that enables the training of reinforcement learning agents to trade equities. Really, it's a core contribution of a few environments that demonstrate stock market dynamics and allow you to then train a reinforcement learning model on top of that. I think it's important to, like, you know, define epistemologically how we even get here from, like, you know, we think there's a stock market, we think it has patterns, we think that there's things that a machine learning model could help us do. And so, you know, trading stocks is a process that is based on logic, strategy, knowledge, intuition, the wind, the weather, you know, like just random dumb luck. But if you had a crystal ball, would that be useful? So if if you're Buff from Back to the Future and he gets the, you know, horse betting book in the 1950s for all the things that are going to happen in the 20th century, yeah, it's true that you can make money if you knew exactly what was going to happen. But there is no crystal ball. And then what you're basically left with is, like, it is possible to sort of have predictive power on what's going to happen to some degree and time series forecast. But even if you have that, it's still probabilistic and you're still going to have a lot of uncertainty. And it's still a complex strategy to decide what to trade with as many instruments and as many assets as you can trade in and actions you can take against those assets. It's not a defined win that even if you knew what was going to happen, it would be easy to take advantage of that. And you'll just have to, like, trust me on that. I try to do it. It's not that easy. Let's go back to that last slide. So you say, well, why not just combine the prediction and what to do as the single actor? And when you get to that is the justification for doing RL. If you can train an agent to observe the market and know your current position, and you tell it what you value, it should be able to trade on your behalf and make cogent decisions that you would probably make as well. And it removes several steps. You know, we have an advisor at our company, and he always tells us if we're talking about a complex problem, he says, well, don't solve parts of the problem, solve the problem. And that's always a North Star for us. That's not always possible technically, but we always try to look for a solution that is the simplest, because usually the simplest solution is the one that's the correct one. Okay, can we go to the next slide? And so if we're thinking about this as an RL problem, we really need to just reframe the problem. You know, we think about actions. What am I going to buy or sell? And in what amount am I going to buy or sell that? Am I going to completely exit? Am I going to liquidate and get out? Am I going to do nothing? Am I going to let the money ride? Am I going to add funds to my portfolio to be able to then buy new things or buy more of what I currently hold? Am I going to take money out because I have a need for liquidity to do something, which is, like, you know, a thing real people do. And then, you know, that's not even considering all of the wild vehicles you can invest with, shorts, longs, margin calls, whatever, all of that stuff. Like, I'm just going to totally elide it, because as a machine learning engineer, it's important to know that it's possible, but it's actually can overwhelm you because there's so much complexity to that whole domain. The second major part of the framing of the problem is the state. You know, what are the positions that we currently hold? How do we represent those to a machine? What is the market doing currently, and what did it previously do? And what exogenous information do I want to pull into this problem space? You know, it is true that an autoregressive model can do a lot of good in a lot of contexts. You know, just looking at the pure signal can help you determine what the signal is going to do in the future. In the stock market, that's true to some degree, but obviously there's a lot of external factors that influence the stock market, and the stock market itself has its own dynamics where different components of the stock market influence the stock market. And then, you know, individual players can influence the stock market as well. So your actions, if you're a big enough player, will actually change the future actions. And so thinking about those as well is critical. And so we represent the actor as really just thinking about this function that takes in the state and produces an action. And it, you know, it looks at what is happening right now, where are the pieces on the board, and what should I do next in response? And you hope that it takes that action in the pursuit of the goals that you teach it to pursue. And that brings us to the last really major component about this problem, which is the environment. And I think that's probably the core contribution of the FinRL project, is what does it look like to encode the game of trading stocks? And how do we do that in such a way that it not only allows us to train a competent model, but to operate out of sample? Because ultimately and inherently, we want to trade stocks at the present time, and the present time has never been experienced except in other dimensions, in the fourth dimension by, you know, globular aliens who traverse all time and space. And so, we're talking about an environment that's going to have to operate out of sample. And so how are we going to represent as close to reality as we possibly can right now? And then I'd like to just call attention to some of these choices. There are lots and lots of choices. What if my model tries to do something that's not possible? It tries to buy more than I can afford. What if I try and sell more than I can afford? I try and liquidate assets that I just don't have. What if I have a certain risk tolerance? What if I don't want to just go for profit? What if I actually want to go for consistent profit? What if I need to put in cash and pull out cash? And how do I actually tell the model, I need you to be this liquid? And what are we going to do about that? What about tax implications? In the United States, there is a very detailed, rigorous set of rules that you must follow, and certain actions will be the goodness of actions is actually impacted by the regulations in your area. So it's important to actually factor that into your strategies and let your model know about those implications in your strategies, because the optimal strategy without taxes is not the same as the optimal strategy with taxes. And so that's incredibly important. And it's not just taxes, there's a whole bunch of these kinds of little frictions to transactions that exist that you need to consider. And then the last one is what about crypto, or what about assets that are not traditional stock market assets? And those are very interesting to consider as well. Let's move on to the next slide, please. And so I think we start to go from that view, that 10,000-foot view of the problem space, and start to really ponder, what is our solution stack? How are we going to actually build the solution? And so I want to talk to you kind of about what's been articulated in FinRL. I will say that we at KUNGFU.AI have been working on other applications of this. I'm not going to talk directly about those, but I do want to talk about what is in FinRL, because it is a great starting point. So the first is RL frameworks. RL frameworks there's a few of them out there, and there's a lot of fierce competition right now, I think, for those. So the first one I want to mention is stable baselines. I think if you were doing RL 2.5 years ago, training Cartpole, OpenAI Gym, Quick Start, you're going to be using stable baselines. It's a solid library. I have no complaints. They did it. Their transition from 2 to 3 was a little bit rough, but it is there for you, and it is solid. It will work. Ray RL Lib is a great choice as well. Ray is surprisingly easy to use and surprisingly effective. And the RL Lib package is actually very fully featured. I can't explain that, but I do know that it is good. And it also has the capability to bring in both TensorFlow and PyTorch models in most cases, and all of the modern frameworks as well. It also is super scalable, so that's a benefit of Ray. And you get other things for free, like multiprocessing across a cluster. That is something that is just magical about Ray. I encourage you to take a look if you have not seen it. Raw PyTorch TensorFlow, you can always go the hard road and just code up your algorithms yourself. I would not recommend that. There's no reason to do that. If you need to customize networks, you can do that with the 2 above I mentioned. I want to throw one out there that was sort of is interlinked with FinRL, which is Elegant RL. Xiaoyang Liu is one of the Elegant RL project founders, and he is a researcher, and he has developed his own framework called Elegant RL. He's showing some fantastic results. I would just caution that the library is new, and so it's going to take some time to get contributors that are going to bring in more buttoned up versions of that library, but it is interesting to see. The second component of the solution stack is really your environment. We talked a little bit in the previous slide about how important it is to have an environment that represents the real world. This is the bulk of the work. You need to develop an environment that is truly representative of your problem, and it brings your problem as close to real as possible, so that when your model does go into the real world, it knows what it's doing. If you imagine Tesla developing self-driving car technology, you imagine that they are training on some simulation and hoping that extrapolates. And so, in cases where sensors fail, or you have glare, or there's 1,000 different cases you have to consider to bridge the simulation to reality gap in your context. And I think that is one of the important developments that FinRL has demonstrated several pieces of. The other one that's important specifically for finance is measurement and features. So financial terms are totally different than the machine learning lexicon. And I think that was actually like an underestimated challenge of working in this domain, is that there are so many terms that have conflicted namespaces and so many terms that are very specific to financial instruments. So picking a package that is reliable and actually rigorous in ML terms and not just finance terms is an understated challenge. I will say that some of the packages have hidden pitfalls that are still relatively unknown to the community. I do plan to contribute some of those best practices and learnings, but it is important to thoroughly vet the math of every indicator you use and to make sure that when you are computing statistics about your returns, you're being very judicious about which packages you use to compute those. And the last one here is feature supplies. You know, it is easy to get market data for the most part. Really good market data is expensive really quick. And that makes sense. You know, Bloomberg terminals have always been very expensive. Pulling in news data, there are a whole bunch of data feeds and data providers. I got to work for a company called Prattle Analytics for a brief moment back in the day. And all they do is like read the Fed statements and try to intimate what they're going to do. And that is $1 million industry, that little thing alone. So I would just say that you can spend a lot of money here getting good features. And what features you add is totally up to you. And then I just want to call out some of these, again, choices. How do you plan to make inference? What does it mean to make an inference? Are we going to be putting a model in like a framework like Quantopian or something like that? Are we going to be building our own and actually having it go and pull some feature repository and make an inference as soon as new data arrives? When do you update models? And how do you know that the model that you put into real life is actually as good as the models that you were training? Like, how do you identify correlation? That would be a kind of a hard challenge. What platform should you integrate with? How do you actually deploy such a model? And then what data providers are most important in my use case? I imagine that there are data providers we haven't even considered that would be tremendously powerful to helping these models achieve their best results. I think it's worth calling out some unfriendly snakes in the grass on this, and maybe it's just worth starting from the highest level. I think in 5 years, we're going to take for granted that reinforcement learning agents trade equities. I think that's going to be a thing we do. I think that we will see a world where robo-advisors translate to reinforcement learning advisors. So I think that's a reality that is coming. But right now, RL is unwieldy and it's challenging to productionize. And it's also really, because it's so challenging to productionize, there is a lot you need to do to sort of verification that involves a lot of compute and a lot of statistics. So without getting into too much detail, that is one path. And, the key takeaways, I think, are evaluation. Evaluation is the most critical thing you will do. I mean, humans are really at our ends, nervous bags of water. And so we have to be conscientious of that reality as we start to productionize things that play with real money. We have to be ready to accept risk and measure risk and think about that. The term that I was looking for is not temporal centrality. It is, stand by for just a second. It is present centricity, which just means that the market is always evolving. The market this year was not the same market as last year, and it will not be the same market as in 2023. And so it's just important to remember that the market evolves and responds and is constantly changing all the time for everything. So that makes this problem hard because almost always you're out of sample, and the out of sample gets more egregiously out of sample the further on we move into the future. RL is also very hard to make consistent because of the latent space of state and the features you use. It is unlikely that your model has ever seen a similar scenario to the one you're showing it at the present time. And so really just thinking about how to make those models very robust in a lot of circumstances is a challenge. And that ties into environments are complicated to design because they have a lot of requirements on them. If you're going to design an environment, you want it to be measurable to your standards, and it needs to be robust to modeling standards. It needs to be capable of developing, producing new, interesting pathways that the model needs to explore, and it's non-trivial. And the last thing to say here is reward functions. Whoa. Reward functions are extremely complicated to think about, even if you're thinking about portfolio optimization. And then you bolt on the fact that you have a model that is completely logical, has a very defined mathematical way of thinking about reward, and you must design this reward function. So there are several examples of reward functions in the FinRL project I'd point you to. It can be as simple as what is my daily returns? What are my yearly returns? It's as complex as I don't want you to have exposure, to X market above certain percentage, above certain number of days, or it could be anything you could think of. And it's really just thinking about how would we have done this in the past with sort of a linear constrained optimization problem. Now let's think about making that a smooth, constrained optimization space into the future. That's really kind of an interesting concept to think about. I think that maybe all my slides. Is that true?
I think so.
Hey, I want to just leave y'all with the thought. I have this really cool poster back here, and it says technology should be in the service of humanity and not the other way around. And just remember that you, as a data scientist, have an onus to do good for the world and for humans. That's ultimately the end all be all. And this is from Facebook Analog Labs, circa 2018 at South by Southwest. So just keep it in mind. Remember that, this is an important mantra to take into all the projects you build. Make sure they do good for humanity.